Behold, the piano. But where did it come from? Meet Bartolomeo Cristofori, born in 1655 in the Republic of Venice. Bart's big break came in 1688 when Prince Ferdinando de' Medici hired Bart to maintain and tune his extensive collection of musical instruments. At the time, it was common for wealthy members of society to sponsor musicians, but Bart wasn't just a caretaker, he was also an innovator. While repairing harpsichords, he had lots of time to think, and eventually his stuff of genius struck. Around 1698, he began working on the first pianoforte, which today is known as the piano. But how does it work? The modern piano is similar to a harpsichord. You just hit the key and it creates a corresponding note. But there are big differences between the two, and the most important one is under the hood. A harpsichord works by plucking the string, like playing a harp. This has a couple of disadvantages. First, a harpsichord can't sustain notes for a long time. Second, it can't play notes louder or softer. A piano works by striking the string with a hammer, and Bartolomeo designed an intricate mechanical system that allows the piano key to hit a soft or a loud note, depending on the player's touch, and also allows each note to play for a longer time. Oddly enough, the pianoforte wasn't an immediate success. In fact, later instrument builders oversimplified his original design because they thought it was too expensive. However, quality eventually won out over the price tag, and the pianos sold around the world today are still based on Bart's original concepts.
A piano is considered to be a percussion instrument because it uses hammers to hit strings. It has 88 keys, 52 that are white and 36 that are black, used to play sharp and flat notes, and high-performance pianos can even have up to 92 keys. There are over 12,000 parts in a piano, 10,000 of which can be moving at a single moment in time. Polish pianist Romuald Kapersky holds the record for the longest continual piano performance at 103 hours and 8 seconds, using absolutely no improv material. The keys of the piano will remain at rest until the external force of the player's fingers is applied. When the player presses down on the key pushes up on the player's finger with an equal and opposite force. When the piano keys are at rest, the force of gravity that is pushing down on them is equal to the force of the rest of the piano pushing up on them, so they have a net force of 0 and are at an equilibrium. The force of the player's fingers on the keys causes them to accelerate. The piano player uses a force on the keys to move them. If you change the force exerted onto the keys and keep the area pressed the same, you can change the pressure exerted on the keys. Notice as well that when you change the pressure, the loudness of the note changes as well. The keys have momentum when they are pressed down and collide with the piano. The piano stays virtually stationary when the key collides with it because of its huge mass and the key's slow velocity. The key and the piano collide without being permanently deformed and without generating heat, so it's considered an elastic collision. The equation P equals m times v, or momentum equals mass times velocity, further backs this to show that the transferred velocity to the piano is virtually nothing. When the key is up, it has more potential energy than kinetic energy, and when the key is pressed down, it has more kinetic energy than potential energy. To calculate an object's potential energy, you multiply its mass, gravity, and height using the equation PE equals m times g times h. To calculate an object's kinetic energy, use the equation KE equals 1/2 mass times velocity squared. The total amount of energy of the keys doesn't change, it just transforms from potential energy to kinetic energy. The piano player's center of gravity shifts as they move around playing the piano's keys.
Turn signals on.
This could be really bad.
Here we go.
That's a red light.
Oh no!
If the piano player's center of gravity extends outside the area of support, they will topple over. For example, if this little girl were to scoot back and her center of gravity extend over the bench, she would fall over. When a key is pressed, it causes a corresponding hammer inside the piano to lift and hit a string, causing a vibration. The frequency of each key varies. A person closer to the piano will hear it at an apparent different frequency than a person further away. If you run towards and away from the piano, this becomes very apparent. The strings will vibrate when energized since they are elastic. Loudness diminishes as sound waves travel away from the piano. Music would be louder to a person sitting in the first row of an auditorium than to a person in the last row. Since sound takes time to travel, a person watching a piano player sitting in this aisle of the auditorium would hear it before a person sitting in this aisle or this aisle.